Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. We're going to unpack something truly fascinating, the brilliant invisible math that literally shrinks our digital world. You know, we send and receive gigabytes of data every single day, usually without a second thought. But under the hood of our phones and laptops, there's this beautifully structured process making the whole shebang possible. Today we're going to demystify it together. So, I want to start by throwing this foundational question your way. How do we shrink massive files without losing a single detail? I mean, it's pretty easy to make a file smaller if you don't mind it getting a little blurry, or if you're willing to toss out some random data. But what if the data is so absolutely crucial that every single piece of information must be perfectly preserved? How does a computer take a massive document, squash it down so it can zip across the internet in milliseconds, and then inflate it back to its exact pixel-perfect original state?
Well, here's our roadmap for answering that today. First, the magic of compression. Second, what is Huffman coding? Third, the four-step algorithm. Fourth, executing the source reduction. Fifth, working backward to encode. And finally, the real-world impact. We're going to break this down step by step.
Part 1. The magic of compression. Shrinking data perfectly.
Okay, so there are a few ways to compress data, but the one we're zeroing in on today relies on a concept called lossless compression. Unlike lossy compression, where you might throw away visual data the human eye can't even notice, lossless methods are totally uncompromising. It's a technique that allows for the perfect reconstruction of the original image with zero data loss. Think about things like medical imaging, architectural blueprints, or technical drawings. A missing pixel in a brain scan, or a dropped decimal in an engineering file, that could be catastrophic. Lossless compression ensures every original detail survives the journey.
Part 2. What is Huffman coding? Short words for common things.
To pull off this perfect zero-loss compression, we use specific algorithms. And one of the absolute MVPs here is Huffman coding. The whole philosophy of Huffman coding is basically captured in this brilliant quote. It assigns short codes to frequent patterns for further size reduction. Actually, if you think about it, it's exactly like how we speak every day. We use really short words for things we mention constantly. Words like I, the, or it. And we save the long, multi-syllable words for complex, rare concepts. Huffman coding does the exact same thing for digital data. It finds the symbols or pixels that show up the most and gives them the shortest possible digital codes.
Part 3. The four-step algorithm. The rules of the game.
So how does it pull this off? Well, Huffman coding operates on a beautifully logical four-step algorithm. Step 1. List your source symbols in order of decreasing probability. Step 2. Combine the lowest two probabilities. Step 3. Repeat that until only two remain. And Step 4. Work backward to assign your zeros and ones. Simple enough, right? Let's keep moving.
Part 4. Executing the source reduction. Following the probabilities.
Reading the rules is one thing, but seeing them in action, that's where it really clicks. Let's look at this reduction phase. We've got 6 original source symbols here, A2 down to A5, listed in decreasing probability. Symbol A2 happens 40% of the time, so its probability is 0.4. Down at the very bottom, A5 only happens 4% of the time, so it's 0.04. Following our rules, we take the bottom two, A3 at 0.06 and A5 at 0.04, and we combine them. 0.06 plus 0.04 gives us 0.1. Boom! We inject that new 0.1 right back into the list. Now we've got a new set of bottom numbers. We grab the lowest two again, in this case A4 at 0.1 and our newly created 0.1, and combine them to make 0.2. We literally just repeat this cascading process, sliding over step by step until the very end where we're left with just two numbers, 0.6 and 0.4. And just like that, the reduction is complete.
Part 5. Working backward to encode, creating the ones and zeros. Okay, here is the aha moment. We've funneled our data down, and now we have to transform that probability math into the actual binary language computers use. Let's trace this backward and build our final digital code. We start with those two final probabilities we just found, 0.6 and 0.4. We assign a 0 to the top branch and a 1 to the bottom branch. Now we just follow the lines backward. Every time a branch splits, we toss a 0 on the top path and a 1 on the bottom path. For example, trace the path for symbol A6. Traveling backward, it rides along the 0.6 branch, which got a 0. Then it splits down the top path of the next branch, picking up another 0. So its final code is simply 0, 0. You trace this backward path for every single symbol, and suddenly, they all have a unique sequence of ones and zeros.
And this right here, this is the absolute mathematical proof that our original goal actually worked. Look at symbol A2.
That's our most common piece of data, showing up 40% of the time. Look at its final code, it's just a single digit, 1. It takes up practically zero space. Now look at symbol A5 way down at the bottom. It only shows up 4% of the time, so the algorithm assigned it a much longer, 5-bit code, 01011. We successfully gave the absolute shortest code to the most frequent pattern. No way, right? It's brilliant.
As a quick side note, depending on the dataset you're squishing down, the final result doesn't just have to be a flat table. It can be beautifully visualized as these branching code trees. They show the exact pathways of zeros and ones, mapping out the precise decisions the algorithm made at every single probability split. It's kind of like looking at the digital root system of the file itself.
Part 6, the real-world impact. Why this math matters.
Okay, so we've walked through the abstract math, we've drawn the trees, we've calculated the codes, but why does the specific process matter to you and me sitting at our laptops? The absolute crucial takeaway is that number, 2.2 bits per pixel. Let me put that into perspective. If we didn't compress that data we just looked at, we'd need a fixed length of 3 bits to represent all 6 of those symbols equally. But because we used Huffman coding to shrink the common ones down to just 1 or 2 bits, the new average length is just 2.2 bits per pixel. We mathematically shrank the entire file's footprint, making it transmit so much faster without losing a single drop of the original information.
And listen, this isn't just some academic exercise. This algorithm is the silent workhorse of the digital age. These internationally sanctioned standards that we rely on every single day, they use Huffman coding. When you look at a high-quality JPEG, when you open a PDF for work, when a photographer saves a huge TIFF file, or even when binary docs are sent over fax using the CCITT Group 3 standard, Huffman coding is in there. It's working behind the scenes, running those exact 4 steps we just learned, keeping your digital life lightning fast.
Which leaves us with a pretty fascinating thought to wrap up our explainer today. We've seen how effectively Huffman coding shrinks our current files. But let's be real, as we move into eras of 8K video, massive virtual reality environments, and just explosive data generation, files are only getting bigger. So as our data needs continue to explode, how will future compression algorithms evolve to keep pace? Will we keep building on Huffman's amazing foundation, or are we going to need an entirely new mathematical language to shrink the digital universe? It's definitely something to chew on the next time you instantly download a massive file. Thank you so much for exploring this with me today, and keep questioning the incredible math that shapes our world.